Hey, and welcome to The Explainer. Today we're talking about something pretty incredible. A massive, invisible force that literally shapes our world. It's like a planetary circulatory system hidden just beneath the waves.
And our story kicks off in, of all places, the middle of the Pacific Ocean with a very strange shipwreck. A container ship gets pummeled by a storm and loses its cargo. But this wasn't just any old cargo. It was 28,000 rubber ducks and other bath toys, all of a sudden just floating in the open ocean.
So for years after this, these little plastic travelers started washing ashore in the most random places you can imagine. We're talking Alaska, Australia, even the Atlantic coast. So the big question is, how? How in the world did they get there? What invisible force took them on this epic global tour?
Well, the answer comes down to something called ocean currents. And the journey of those rubber ducks, it gives us a perfect accidental map for understanding the powerful movers that operate right on the ocean's surface.
So, what exactly are we talking about here? The simplest way to think about it is that ocean currents are like giant rivers flowing inside the ocean itself. They're always on the move, pushed along by a few key forces. We're going to start with the ones that gave our rubber duck friends their wild ride.
The currents right at the surface are the speedsters of the system. They make up about the top 10% of all ocean water, going down to maybe 400 meters. And the main engine for these things? It's the wind. Just as wind blows across the surface, it literally drags the water along with it. This creates these huge flowing streams that basically became highways for all those lost toys.
But here's the thing. These currents don't just move in a straight line. I mean, if the Earth stood still, maybe they would. But since our planet is constantly spinning, it actually bends the path of the currents. This is a phenomenon known as the Coriolis Effect.
And all this constant bending from the Earth's rotation, it forces the currents into these massive, swirling, circular patterns. We call these giant loops gyres. This is exactly why stuff, like our ducks, or unfortunately trash, can get trapped in certain areas, forming those huge garbage patches you hear about.
And they even have a predictable spin, which is pretty cool. Up in the northern hemisphere, they all spin clockwise. Down in the southern hemisphere, they do the exact opposite, counterclockwise. It's the simple, really elegant pattern that governs the whole top layer of our planet's oceans.
But remember, that's just the top 10% of the story. So what's going on with the other 90% of the ocean? Well, way down in the dark, cold depths, we find a totally different system at play, the deep, slow conveyor.
It's really important to get that there are two separate systems working here. You've got the fast, wind-driven currents up top. But beneath them, in that vast, deep ocean, you have the deep currents. And they're not moved by wind, they're moved by density. And man, are they slow. The engine that drives these deep currents has a very fancy scientific name, thermohaline circulation. But let's just break that down, because it's actually pretty simple. Thermo means heat, right? Like a thermometer. And haline just refers to salt. So it's a circulation that's driven by heat and salt. That's it.
Here's how it works. Picture this. Warm water from the equator travels up towards the poles. When it gets there, naturally, it cools down. And as sea ice starts to form, it pushes the salt out, leaving the leftover water extra salty. So now you've got this water that's both cold and really salty, which makes it super dense. And what does dense stuff do? It sinks. It plunges deep into the ocean, and that's what starts its long, slow journey back toward the equator.
This whole worldwide system of water sinking, traveling, and eventually rising back up creates what scientists perfectly named the Global Conveyor Belt. And it's the perfect description, right? It's this slow-moving but incredibly powerful current that connects every single ocean on Earth, from the surface to the very bottom.
The scale of this thing is it's mind-boggling. To give you some perspective on how slow it is, a single drop of water can take a full 1,000 years to make just one loop on this conveyor. I mean, a journey that might have started when the Vikings were sailing could be just finishing up today. It's wild.
Okay, so we've got these two huge systems, fast on top, slow on the bottom. But why does any of this really matter to us? Well, because this whole setup is nothing less than our planet's climate engine.
Think about it this way.
If the Earth had a circulatory system like our bodies do, the ocean currents would be it. They're constantly moving vital heat away from the equator towards the poles, and they pull nutrients up from the deep sea to the surface, which supports entire ecosystems.
A perfect example of this is a part of the conveyor belt called the Atlantic Meridional Overturning Circulation. I know, it's a mouthful. Let's just call it the AMOC. The AMOC is basically a giant heat pump. It carries huge amounts of warm tropical water northward into the Atlantic, where it releases all that heat and dramatically warms up Western Europe.
If you want to see the real-world impact, just look at London and Calgary. They're at the exact same latitude, but their climates couldn't be more different. In winter, Calgary is absolutely freezing, while London is pretty mild. So what's the difference maker? It's the AMOC acting like a giant radiator for all of Western Europe.
The sheer amount of energy this system moves is unbelievable. The heat that the AMOC carries is equivalent to the energy output of about 1 million power plants. It is truly one of the most fundamental forces shaping the climate that we all live in.
But this absolutely vital climate-regulating system, it's now facing a really serious threat. And it's one that could have massive consequences for every single one of us.
Here's the chain reaction we're worried about. As the planet warms up, ice sheets in places like Greenland are melting faster and faster. This is dumping enormous amounts of cold, fresh water into the North Atlantic. Now, remember how the engine works? Salty water sinks, but fresh water is much less dense, so this fresh layer can end up sitting on top like a lid, preventing the salty water from sinking, and that could slow down or maybe even stop the entire engine of the conveyor belt.
And we're already seeing some pretty strange signs. Scientists have found this area in the North Atlantic they've nicknamed the cold blob. It's one of the only places on the entire planet that has been consistently getting colder over the last century, while almost everywhere else is getting warmer.
And that leads to the critical question. Is this cold spot the first piece of hard evidence that less warm water is being pulled north? Could this be the first tangible sign that the AMOC, our planet's great climate engine, is already starting to weaken?
The ocean's currents are, without a doubt, the lifeblood of our planet's climate. It's this delicate balance of heat and salt that keeps our world habitable. The evidence is telling us that this system is under stress, and that leaves us with one final and really crucial question to think about. What will it take to protect it and to keep it running?